All right. Now, this next notion that I want to discuss is actually a really, really, really important notion, both in math and in computer science. So be careful. Okay, this is kind of a hard concept. So what we're describing is a well ordering, right? So remember, what does the ordering part mean? Okay, that just means reflexive, antisymmetric, and transitive. Okay, that's all that word means, right? You know, it's ordering means those three things. Okay, the question is, what is a well ordering, right? That's what we're trying to define, and what we want is this property right here. Okay, that it is impossible to have an infinite descending chain. Okay, so what is an infinite descending chain? It's actually easiest to show you with an example, so let me do that. Okay, let me start with the number 7. Okay, and I want to find a number that is strictly smaller than it. Okay, so I'm going to put down 5, right? And you see it has that property. Because I'm talking about orderings, I'm going to say less than or equal to, even though I actually don't allow equal. Okay, all right, so let's make it smaller. 1, 2, right? Let's make it smaller. 1. Let's make it smaller. 0. Okay. Now, I didn't tell you what numbers I was using, right? Are we talking about the naturals? If we are, then you know that I can't make it any smaller than that. Okay, I'm done, right? And what that means is that if I start with, let's say 7, right? Then all descending chains, this is what's a descending chain, right? It's a bunch of numbers that keep getting smaller, right? All descending chains are at most 7 long, right? Because 7, 6, 5, I guess 8, right? Because we go to 0. Okay, so that's an important kind of concept, right? If this is the case, right, all descending chains have at most some fixed number, then we say that it's a well ordering, right? It is impossible, right? Here's the definition, right? There are no infinite descending chains, right? So for the naturals, we have a well ordering. But let's try to repeat the same example, but now over to integers, okay? So 7 is greater than or equal to 5, is greater than or equal to 2, is greater than or equal to 1, or equal to 0. But notice what I can do now. This is minus 2, minus 4. And here, what we have is an infinite descending chain. All right. Now, I want to be clear. 1 less than or equal to 1, 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 and so on. It's not an infinite descending chain. It's not actually descending. It's staying in place. Okay. So here, that's why we have this rule: x sub I is not equal to x sub j when I is not equal to j. Okay. So keep that in mind. Otherwise, you'll come up with counterexamples that aren't quite right. Okay. So here, this is a finite chain. Here is an infinite descending chain, right? So what does it mean to be well ordered? It means that this never happens, right? That's what it means to be well ordered. So in here, for the naturals, we have a well ordering. Over the integers, not well ordered, with less than or equal to. Okay, it's possible that there's a different relation that actually orders them as a well ordering, and in fact there is. Okay, but not less than or equal to is not that. Okay, so that's what I mean by well ordering, and again, I think it'll help you just kind of see some examples, right? So there's the one we talked about. Over the integers, it doesn't work. Over the naturals, less than or equal to does work. Okay. Now, here's an interesting property. Okay, and the interesting property is this: an ordering is a well ordering if and only if every non-empty subset contains a least element. Okay, so what does that mean? Well, here's the set, right? It's non-empty, so it's got at least one element, right? And what we want is it's got lots and lots of points there, right? Lots of elements. And one of those elements is going to be the least. Okay? Here's an example of something that's not well ordered, right? And I have a whole bunch of points here, right? And here is my least element. right? That's no good because the least element actually doesn't belong to the set. Okay, so it turns out that it's actually real easy to prove this. So let's go ahead and do that. This is an if and only if, so we have two parts, right? So let's start by showing if we have a well ordering, then all non-empty subsets have to have a least element. Okay, so let's find a non-empty subset as 0, right? This should be S0 not equal to the empty set. Okay, and that means that I can now choose and x naught that belongs to it. That's what it means to be non-empty, right? It's got to have at least one. Okay, so now think of this set. I want to think of all the set of x's, right, such that x belongs to S naught and x is less than or equal to x0. Okay, this is that element that I picked, right? Okay, right. I can always kind of arrange them, right? Because I have a well ordering, right? So I can write these elements down as x naught, which is greater than x1, which is greater than, and so on, right? But it's a well ordering, so I can't have an infinite, right? This has to be a finite chain. So it's going to stop at some point, and let's say that is x sub n. Okay, so that's what we have here, right? Well, x sub n now is going to be a least element in S naught. Okay, this right here is a least element. Now, to be clear, that doesn't mean that it's the smallest element in S naught. You see, if we don't have a total ordering, it's possible that there's another element that also has that property, right? So, you know, we don't quite know that it's the smallest element, but what we do know is that there's nothing smaller than it. That's why it's a least element, not the least element. Okay, so yeah, we find a least element, and that's what we're looking for. Okay, so if it's a well ordering, there has to be a least element. Why? Just pick something, follow a chain. Oh, it's finite, so when you stop, by definition, there's nothing smaller because we followed an entire chain. Okay, so let's go the other way. Okay, so what we'll do is we'll look at an ordering that has this property. Okay, and every subset of S has a least element. Okay, all right. So if that's the case, here's what we'll do. Okay, suppose that we have a chain, x1, x2, x3. Right? It's just some infinite sequence. Okay. Now, is it possible that this is actually an infinitely descending chain? Right. I mean, it's a sequence, right? But can it be descending? And the answer is no, right? Because I can think of a set that has those items in it, right? And then there is a least element. And let's say that that's x sub k, right? Well, then I can't form an infinite chain, right? You know, because I'm gonna stop when I get to xk. Okay. By the way, if you're thinking, yeah, but what if, you know, what if what happens is this: we start here, we go there, you know, there's an infinite chain, and here's x sub k, right? That still can't happen because I can pull the same trick, right? Just think of that sequence, right? Except take x sub k out, right? There's still a least element. So anyway, so what we have here is that it's as long as we have the least element property, we can't generate infinite descending chains. If we don't have infinite descending chains, then every set has a least element. Perfect, right? So we have another way of defining what it means to be a well ordering. And by the way, I want to say this. Some textbooks actually define a well ordering to be an ordering such that every non-empty set has a least element, right? It doesn't actually matter which way you do the definition, as long as you can have both properties, no chains and least element. For our purposes, no chains is much more important. That's why I'm using that definition. Okay. I keep saying that they're important. Why are they important? Okay. The reason is that there's a lot of data structures. Okay, and here are some of the data structures that I'm talking about: lists, trees, and so on. That happen to be well ordered. Okay, so for example, let's do lists. A list looks like this: A1, A2, A3, and it's a finite list, so it goes up to A sub n. Okay, well, if I look at a sublist like A2, A3 up to A sub n, right? So this is actually a sublist of that one, right? You can see that this is a well ordering because if I just keep doing this, eventually I run out of elements, right? Okay, so so lists are actually well ordered under this simple principle of inclusion. Think of trees, right? I'm going to have a finite tree. Okay, so again, we have this property. Here's a subtree, right? And it's smaller than that one. Well, here's a subtree of that one. And I finished, right? I got to the leaf. There are no more subtrees. That's as small as you can get. Here is a least element. Okay, and there are no infinitely descending chains because our trees are finite. So these data structures actually come up all over the place in computing, right? I mean, we've built a whole discipline out of them, and we're going to use the fact that they're finite, that there are no infinite descending chains, equivalently that there is, you know, every set has a least element, to do proofs. Okay.